Hello students, welcome back. In this part, we are going to discuss about the various types of defects present in a crystal and in what way they will affect the properties of a crystal. So let's start. Now let's understand about the imperfections in solids. It is also known as defects in crystals. So what are all the defects in crystals and how they affect the properties of the crystals? Okay. An ideally perfect crystal is one which has the same unit cell and contains the same lattice points throughout the crystal, right? So if you take an ideally perfect crystal, that is going to have the same unit cell and contains the same lattice points throughout the crystal. And the term imperfection or defect is generally, it is used to describe any deviation from the ideally perfect crystal, right? So if anything, if in any way any deviation is occurring from the ideally perfect crystal due to any reason, then all these are known as imperfections or defects. Okay, so defect or imperfection. So defects in solids or imperfection solids can be categorized into three types. One is impurity defects, second is stoichiometric defects, third is non-stoichiometric defects. So in this part, we will only discuss about the stoichiometric defects which are important for JEE purpose. And under stoichiometric defects, we have Schottky defect, we have Frankel defect, we have vacancy defect, and we have interstitial defect. So let's understand these four defects one by one with examples. So stoichiometric defects. So what is meant by stoichiometric defects? These are the defects that do not disturb the ratio of cations and anions. The ratio of cations and anions is still going to be the same even though these defects are present in the crystal. So the compounds in which the number of cations and anions are exactly in the same ratio as represented by their chemical formula are called stoichiometric compounds. Okay, so I will repeat this once again. The stoichiometric compounds are the compounds in which the number of cations as well as anions are exactly in the same ratio as represented by their chemical formula. So whatever the chemical formula representation they have, so even after the defect, the number of cations, the ratio of number of cations and anions is still going to be the same in stoichiometric compounds, and the stoichiometric defects which does not alter the stoichiometry of the compound. So that's why the name is given as stoichiometric defects. And these defects are four types. One is Schottky defect, Frankel defect, vacancy defect, and interstitial defect. Okay, so let's discuss about these four defects one by one. So first is Schottky defect. So what is Schottky defect? This defect happens when equal number of cations and anions are missing from the lattice of an ionic crystal of type AB. Okay, so if I take a crystal of AB type which is containing cations and anions, so in this defect equal number of cations and anions will miss from the crystal. Okay, so if one cation is missing, then one anion is going to be missed, and if two cations are missed, then two anions are missed. So the equal number of cations and anions are going to be missed. They are missing from the lattice. So here if you see, this is one cation is missing and one anion is missing. So if two cations are missed, then two anions are missed, like that. So this defect is shown highly by any compounds which have high coordination number and small difference in the size of the cations and anions. So if there is no much difference in the size of cation and anion, then there is a more probability that this defect is going to happen. And this defect is also very common in compounds, in any compounds which have high coordination number. So a few examples of such ionic compounds which show this kind of defect are sodium chloride, potassium bromide, and cesium chloride, etc. Okay, so this is about Schottky defect, and let's see what are the consequences of this defect. What are the changes it brings into the crystal? Okay, the first is here, as the number of ions decreases of this defect, because of this defect, the mass decreases, but whereas the volume remains same. So here the ions are missing from their lattice sites. So since the ions are missing, the number of ions are decreasing. So obviously the mass of the crystal is going to be decreases. Okay, but the volume still remains same. So mass decreases whereas volume remains constant. So as a result, the density of the crystal is going to decrease, because we know that density is equals to what? It is equals to mass by volume. So density is equals to mass by volume. So volume is same, but mass is decreasing. So as a result, the density is going to be decreasing. So density of solid decreases, and the crystal begins to conduct electricity to a small extent by ionic mechanism. The crystal, it begins to conduct electricity to small extent by ionic mechanism, and the presence of too many voids. So if too many cations and anions are missing from the lattice sites, because of the presence of too many voids, the lattice energy is going to be lowered. So as a result, the stability of the crystal is going to be decreased. Okay, so this defects destabilizes the crystal if too many voids are present, if too many cations and anions are missed from their lattice sites. So these are all the consequences of the Schottky defect. So let's understand this Schottky defect from a video demonstration. So let's see a video. So Schottky defect. So if you see in this Schottky defect, we have an NaCl crystal, right? This is NaCl crystal, and here we have a chloride ion which is negative, and here we have a sodium ion. So sodium ion is missing from its lattice site, and even the chloride ion is also missing from its lattice site, right? These two are unoccupied. So these two sites are known as lattice vacancies, right? Because ions are vacant there, the vacant space. So here, since one ion is missing, one positive ion is missing and one negative ion is missing, so as a result, the crystal is going to be neutral, right? Because the total number of positive ions are missing equal to the total number of negative ions missing. So here one sodium ion is missing and one chloride ion is missing from its site, so which are known as lattice vacancies. Okay, so the Schottky defects, it appears generally in any crystals in which the positive and negative ions do not differ much in size. As I already discussed that this defect happens in crystals where there is no much difference in the size of cation and anion. So let's go to the next defect, that is Frenkel defect. It is one of the stoichiometric defects. So this defect occurs if an ion is missing from its correct lattice site and is occupying an interstitial site. That means ion, instead of occupying its own site, it will go and it will stay in some other interstitial site. So such type of defect is known as Frenkel defect, or it is also known as dislocation defect, because the ions are dislocated. Okay, so that's why this defect is also known as dislocation defect. So let's understand this with an example. So here this is the site of the positive ion, but this positive ion is missing from its own lattice site and it is occupying this interstitial site. This is interstitial site and creating a defect in the crystal, and such type of defect is known as Frenkel defect. And if you see, the small ion is dislocated, right? So generally the cation is smaller, so that's why, since cations are usually smaller, so this defect is, it is more common to find the cations occupying the interstitial sites. Okay, cations occupying the interstitial site. Electrical neutrality as well as stoichiometry of the compound are maintained, right? So here the electrical neutrality as well as the stoichiometry of the compounds are maintained, because here no ion is leaving from the crystal. So that's why the electrical neutrality is maintained and even the stoichiometry of the compound also maintained. So this type of defect is present in ionic compounds which have low coordination number, and when there is a large difference in the size of cation and anion. So if there is a large difference in the size of cation and anion, then in such crystal this defect is more common. And compounds having high polarizing cation and easily polarizable anion will have a more tendency, such type of crystal will have a more tendency to show this defect. Okay. So a few examples of ionic compounds which are exhibiting this defect is silver chloride, silver bromide, silver iodide and zinc sulfide, in which the size of the cation and anion is high. Okay. Let's see some of the consequences of the Frenkel defect. Since here no ion is missing from the crystal lattice, they are simply dislocated. Instead of staying in its own place, the cation will stay in some other place, in some other interstitial space. So here no ions are missing from the crystal lattice, so therefore no change in the mass, no change in the volume, and as a result there is no change in the density of the solid. Okay. The closeness of like charges tends to increases the dielectric constant of the crystal, and the crystal also conducts electricity to a small extent by ionic mechanism. So these three are the consequences of the Frenkel defect. So let's understand this defect with a video demonstration. So this is Frenkel defect. So Frenkel defect is generally shown by ionic compounds in which there is a large difference in the size of cation and anion. You can see the cation is smaller and anion is bigger in size. So here the cation is missing from its own lattice site and it is occupying this site. I repeat this thing. So here it is missing. This is the original site where it has to stay, but here it is occupying this interstitial position, some other position in the crystal. So such type of defect is known as Frenkel defect. Yeah, this is the interstitial site it is occupying here. So this is about the Frenkel defect, which is simple. Let's move to the next defect, that is vacancy defect. So it occurs when some of the lattice sites are vacant. So here you can see this lattice site is vacant. So such type of defect is known as vacancy defect, and this results in the decrease in the density of the substance because here ions are missing from their sites. And this defect can also develop when a substance is heated. Okay, so this is vacancy defect, which happens when the ions are missing from its sites. Next is interstitial defect. Interstitial defects occurs when some constituent particles occupy an interstitial site, right? So instead of staying in their own site, they occupy some interstitial site. So such type of defect is known as interstitial defect, and this defect increases the density of the substance, right? So some other particle is staying in the solid, so which is increasing the mass and which increases the density of the substance. So this is all about the stoichiometric defects, Schottky defect, Frenkel defect, vacancy defect as well as interstitial defect. So in these four defects, Schottky and Frenkel defects are very, very important, and their consequences are also very, very important for competitive examinations. Okay. So students, in this part we mainly covered the stoichiometric defects, under which we discussed about the Schottky defect, the Frenkel defect, the vacancy defect, and finally interstitial defect. We also discussed how these defects affects the properties of a crystal. In our next part, we will discuss about some previous year's JEE questions. So keep watching.